Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you. Echoes through the air. How radio waves carry sound. Radio waves, an integral part of the electromagnetic spectrum, have revolutionized communication by enabling the wireless transmission of sound and data over vast distances. These waves operate by converting sound into electromagnetic signals that travel through the air and are received and interpreted by a compatible device. The process is grounded in physics and technology, requiring a delicate interplay of signal generation, modulation, transmission, and reception. At the heart of transmitting sound via radio waves is the conversion of acoustic vibrations into electrical signals. A microphone captures sound waves and converts them into an electrical waveform that mirrors the original sound's amplitude and frequency. This electrical signal, which carries the audio information, is too weak to be transmitted over long distances on its own, so it is combined with a carrier wave. The carrier wave is a steady, high-frequency electromagnetic wave that serves as the medium for the audio signal. To transmit sound, the audio signal modulates the carrier wave, altering its characteristics in a way that encodes the audio information. The two primary methods of modulation are amplitude modulation, AM, and frequency modulation, FM. In AM, the amplitude of the carrier wave varies in proportion to the sound signal, while its frequency remains constant. Conversely, in FM, the frequency of the carrier wave fluctuates according to the audio signal, but its amplitude remains unchanged. Each method has its advantages. AM is simpler and can travel longer distances, while FM offers better sound quality and resistance to interference. Once modulated, the radio wave is amplified and sent to an antenna, which radiates the wave into the atmosphere. The antenna's design and size are crucial, as they determine the efficiency of the transmission and the range of the signal. As the radio wave propagates, it travels at the speed of light, carrying the encoded sound across vast distances. This transmission process relies on the wave's ability to reflect, refract, and diffract through the environment, ensuring that the signal reaches its destination even in complex terrains. The next part will delve into how these transmitted waves are captured, decoded, and converted back into sound, exploring the intricacies of receivers and the challenges posed by interference, signal degradation, and modern digital enhancements to traditional radio communication. Stay tuned to uncover the other half of this remarkable process. The journey of sound carried by radio waves continues as the transmitted signals are captured and decoded into audible sound by radio receivers. A receiver, the counterpart to the transmitter, is designed to detect and interpret the modulated carrier wave that contains the sound information. This process is a marvel of engineering, requiring precision to ensure the original audio signal is faithfully reconstructed. When the radio wave reaches the receiving antenna, it induces a small electrical current in the antenna's conductive material. This current is a replica of the modulated wave sent by the transmitter, though significantly weaker after traveling through the air. The antenna captures waves within its designed frequency range, filtering out other signals to focus on the intended broadcast. The captured signal then undergoes amplification to strengthen it for further processing. Decoding the modulated wave involves a process called demodulation. In this stage, the receiver separates the audio signal from the carrier wave, effectively extracting the original sound data. For AM signals, this involves detecting changes in amplitude and discarding the carrier's constant frequency. FM signals, on the other hand, are demodulated by measuring the variations in frequency while ignoring amplitude changes. This demodulation restores the audio waveform to its original form, ready to be converted back into sound. After demodulation, the recovered audio signal is sent to the receiver's speaker system. Here, the electrical signal is converted back into mechanical vibrations that replicate the original sound waves. The speaker's diaphragm moves in response to the electrical signals, compressing and decompressing the air to produce sound that mirrors the original source, whether it's music, speech, or other audio content. Radio communication, however, faces numerous challenges that must be managed for optimal performance. Interference from other electronic devices, weather conditions, and geographical obstacles can distort or weaken the signal. Noise, which refers to unwanted electrical signals that blend with the desired transmission, can also degrade audio quality. Engineers address these challenges by refining receiver designs, using filters and circuits to enhance signal clarity, and implementing error correction techniques in modern digital radios. The process of converting sound into radio waves and back again is not limited to analog systems. In recent years, digital radio has introduced new layers of complexity and efficiency. By digitizing audio signals, broadcasters can compress and transmit higher quality sound, while receivers employ advanced decoding algorithms to reconstruct the digital data. Digital transmission also allows for additional features, such as metadata for station identification, song titles, and program information. In the next and final part, we will explore the broader implications of radio wave technology, its historical impact on communication, and its evolving role in a world increasingly driven by digital innovation. Stay tuned as we delve into the enduring significance of this transformative technology. The significance of radio waves in transmitting sound extends far beyond the technical processes of modulation and reception. Since their discovery in the late 19th century, radio waves have fundamentally transformed the way humans communicate, bridging vast distances and enabling the near-instantaneous sharing of information. This technology has not only revolutionized personal and public communication but has also shaped the cultural, political, and scientific landscapes of the modern world. Historically, the advent of radio broadcasting marked a turning point in mass communication. In the early 20th century, radio became a powerful tool for disseminating news, music, and entertainment. It connected people across regions and countries, creating a shared experience that transcended geographic boundaries. During critical moments in history, such as wartime broadcasts or significant cultural events, radio served as a lifeline for information, uniting communities and shaping public opinion. Even today, in remote areas with limited internet access, radio remains a vital medium for reaching populations and fostering connection. Scientifically, the study of radio waves has spurred advancements in numerous fields. The same principles that allow sound to be transmitted wirelessly have been adapted for applications in television, satellite communication, and cellular networks. Radio waves also play a crucial role in scientific research, particularly in astronomy, where they are used to study celestial objects and phenomena invisible to optical telescopes. Radio telescopes have revealed insights into the structure of the universe, from detecting distant galaxies to unraveling the mysteries of cosmic microwave background radiation. As technology evolves, the role of radio waves continues to expand. Digital radio and internet-based streaming have redefined how audio content is consumed, offering higher quality sound, greater accessibility, and a wealth of interactive features. Moreover, the principles of radio wave transmission underpin modern wireless technologies, from Wi-Fi to Bluetooth, enabling the seamless connectivity that defines today's digital age. The integration of radio technology with artificial intelligence and machine learning promises to further enhance communication systems, paving the way for innovations such as intelligent networks and adaptive broadcasting. The enduring legacy of radio waves lies in their versatility and adaptability. They have not only transformed sound transmission but have also opened new frontiers for exploration and creativity. Whether through traditional AM/FM broadcasts, digital platforms, or cutting-edge wireless communication, the humble radio wave continues to connect humanity, fostering understanding, innovation, and progress.